One of the most important variables in meteorology is pressure, and pressure is simply just the force of the air that's pushing down on objects. And pressure tends to decrease as you go up into the atmosphere. The pressure we experience down here at the surface is much, much greater than that, say at 8, 9, 10 miles above the surface. Pressure decreases with height. In meteorology, the way that we analyze the atmosphere is by selecting a bunch of different levels at which the pressure is the same and analyzing atmospheric features on those constant pressure levels. These are called mandatory levels, and there are a bunch of different mandatory levels, just a few of which, though, are most important in day-to-day severe weather forecasting. These are the surface, 850 millibars, 700 millibars, 500 millibars, and 300, 250, or 200 millibars. This is your upper level atmosphere map, and it depends on which time of year you're looking at as for which map you're going to use. The 300 millibar map is used in the winter, the 200 millibar map is used in the summer, and the 250 millibar map is used in the fall or the spring. But overall, that's just your upper atmosphere map. So those are our mandatory levels that we use in meteorology. These are all given in millibars, as we said, which is just the basic unit of measure for pressure in meteorology.
We're giving away a 2027 Storm Chasing Tour seat for free. That's a $5,400 value. Join our Discord community to enter. Link in the description.
So let's dive into these mandatory levels and show you why each one of these is important in severe weather forecasting and what you should be looking for when you're analyzing these upper air maps during a severe weather forecast. Let's start off with perhaps our most important mandatory level, 500 millibars. Most forecasters use a top-down approach to forecast severe weather where they start with the highest level of the atmosphere and go all the way down to the bottom in succession. I like to start at 500 millibars because it really gives us a good idea of the overall background pattern, and we can make a lot of assumptions just by looking at the 500 millibar map. First, let's just give you a brief overview of what all of these symbols and lines mean. Basically, these blue barbs here, these are wind barbs. So basically it tells us the speed and direction of the wind. These barbs consist of flags, full staffs, and half staffs. Each flag is worth 50 knots. The winds in the upper levels of the atmosphere are measured in knots. The full staffs are worth 10 knots, and the half staffs are worth 5 knots. So in this example here, this would be a 50 plus 10 plus 5 knot wind, which is a 65 knot wind. And the direction of the wind is assumed by going through the flags and staffs toward the end of the barb, or toward the center of the station. So this would be a 65 knot wind out of the southwest. So that's how those wind barbs work. These lines here, these solid black lines, are not pressure contours. They are contours of equal geopotential height. Let me explain what geopotential height is. Recall that all of these individual weather maps in the upper levels of the atmosphere, each mandatory level, is a constant pressure surface. So it's basically a surface where the pressure is the exact same across every point on that surface. So for example, on the 500 millibar map, every point on this map is at 500 millibars. So we can't really use pressure to determine areas of high and low pressure like we would at the surface. We'll talk about the surface map here in just a bit. So we have to use a variable called geopotential height. Geopotential height is the height of a constant pressure surface above mean sea level. And geopotential height varies based on variables such as temperature. So in some locations, the 500 millibar surface, for example, would be lower than it is at other locations. As you can see here, the height actually varies across the entire 500 millibar constant pressure surface. This is what geopotential height is, and this is how we can measure how changes in the atmosphere are occurring on these constant pressure surfaces. On the 500 millibar map, we're really looking for features called troughs, and troughs are these downward bends or downward kinks in the geopotential height contours. So you see here that the geopotential height contours are kind of bent like a ski jump or a skate ramp. And so that's how you can think of these troughs. It's just like a skating ramp. The winds go through the ramp, they accelerate toward the base of the ramp, and then they eject into the other side of the trough, other side of the ski jump. And That other side of the ski jump is where you want to be for your highest chance of robust severe weather. That is called the exit region of the trough. So if we were to draw an axis from the center of the trough through the base of the trough, so basically through the base of the ski jump, we would want to be on the right side of the axis. So all this area over here on the right side of the axis is the exit region of the trough. And the exit region of the trough is the most favored area within the trough for upward motion or lift. Lift is maximized in the exit region of the trough. Lift is one of our most important ingredients for severe weather. And again, in the exit region of these troughs, that's where lift is maximized. And so the exit region of these troughs is where the chances for severe storm initiation is greatest because the lift is maximized in that portion of the trough. Now, which way the trough is oriented is also important. What happens in the mid and upper levels of the atmosphere, 500 millibars is considered the mid levels of the atmosphere. What happens at these levels dictates what happens in the low levels of the atmosphere, and the orientation and geometry of troughs can give us an idea of how robust the response is going to be at the low levels, because whatever happens in the mid and upper levels of the atmosphere dictates what happens in the lower levels of the atmosphere. So going back to our trough axis here, this dashed pink line basically through the center of the trough down through the base of the quote-unquote ski jump. When this axis is tilted back to the left, like it is here, this is called a negatively tilted trough. Negatively tilted troughs tend to produce a more intense low-level response, which means a more intense surface low or low-level cyclone development. Again, we'll talk about the low levels here in just a bit and the surface here in just a bit. But these troughs tend to induce surface low development, especially when they go over the higher terrain areas like the Rockies. So when these strong winds go through the base of the trough and go over the higher terrain of the Rockies, they tend to induce surface low development, surface low pressure development. When you have a negatively tilted trough, that surface low pressure development tends to be more intense than a positively tilted trough, which is when the axis tilts toward the right. So in this example here, we have a very robust trough across the western U.S. Its axis here goes from basically northern Nevada down through the desert southwest into western Mexico. It's tilted back toward the left, so this would be a negatively tilted trough. So we would expect, as this trough moves into the central U.S., that we would see pretty robust surface cyclone and low-level cyclone, low-pressure development in the low levels here in the exit region of that trough. And low-pressure development tends to occur in the exit region of these troughs. So to summarize, at 500 millibars, we want to be looking for these troughs in the geopotential height contours, and we want to focus on the exit region of these troughs for the greatest chance for severe storm initiation because lift is maximized in the exit region of these troughs. Now let's go up to our 300, 250, and 200 millibar maps. Again, these basically show the exact same thing, but which map you use or want to favor depends on what time of year you are analyzing storms in. So for example, the 300 millibar map is best suited for the colder times of year, so the winter and early spring. The 200 millibar map is best suited for the warmer times of year, such as the summer. But most of the time for your spring and fall severe weather setups, which is of course the main time frame for your most robust severe weather events in the United States, the 250 millibar map is going to be a good choice. And so we're going to use a 250 millibar map for this example here. Just like at the 500 millibar level, we want to be looking for those troughs, those downward kinks, and on this particular map source, these are not geopotential height contours here, these solid lines. These are actually streamlines. It basically just, those are lines that follow the wind direction. It's basically going to show you the same thing as geopotential height contours would, as geopotential height contours tend to follow the wind as well. It's just another way to depict which way the wind is blowing along with the wind barbs. On the upper level maps here, the 300, 250, and 200 millibar map, this source tends to shade in the wind contours. You see the scale over here on the left. So your blue colors are 75, 100, 125 knots, and your purple colors are any winds above 150 knots. The winds at the upper levels of the atmosphere are much, much stronger than they are in the lower levels of the atmosphere in most cases, especially near troughs. Just like at the 500 millibar level, we want to be looking for these troughs, which are often associated with jet streaks. Jet streaks are these little areas of enhanced flow that tend to round the base of the trough. With this particular one, we see a couple of different jet streaks, this one near the base of the trough and this one back here on the back side of the trough. These are just belts of enhanced flow that move through the trough, and just like at 500 millibars, we want to be in the exit region of these troughs and jet streaks. So we want to be right out ahead of the trough and jet streak. If we were to draw again, once again, our axis through the trough and jet streak, we would want to be right out ahead of that for our best chances for severe weather. Now, I will note something I did not mention before. These are maps from the morning of a particular severe weather event in the past. So always keep in mind, if you're looking at maps on the morning of a severe weather event, that these features are going to translate. They're going to move a little bit with time during the day. So even though our exit region of the trough is located here over the kind of Four Corners region northward, that would probably translate over into the Central Plains by the afternoon, which is when severe storms are often favored to initiate. So just keep that in mind when you're analyzing maps, especially in the morning of an event. These features are not static. They are going to move with time. So again, troughs are what we want to be looking for at 300 millibars, and we also want to be looking for a feature called diffluence. Diffluence is just the spreading apart of the winds in the upper levels of the atmosphere. What diffluence does, basically when winds spread apart from one another, it creates kind of a void. There's really kind of, you can think of it as no air left in between when these winds are spreading apart. And Mother Nature does not like that. So what is done to try to compensate for this is air is brought up from below the low levels of the atmosphere upward to fill this void. And that's how we get rising motion or lift or ascent, as we call it, to fill that void. And the rising motion is a favorable thing for initiation of severe storms. So that diffluence, when we have ample diffluence aloft, when the winds in the exit region of a trough spread apart, that tends to induce ample rising motion or lift, which can help initiate severe storms in given severe weather environments. So in this example here, our exit region of the trough is going to be again on the right side of the axis of the trough. So we're looking over in here in the Rockies region, and you can see that we have pretty ample diffluence aloft in the exit region of this trough. The winds here over Wyoming are more out of the almost due south, whereas the winds over the central high plains here over southwest Kansas are out of the southwest, almost west-southwest. So you can see those winds are really spreading apart there in the exit region of the trough, which means we have quite a bit of ability for air to rise in this region from below, and that lift would be very favorable for severe storm initiation in this environment. Down at 700 millibars, we want to be looking for things called shortwaves. Shortwaves are basically just small-scale troughs that rotate through the main larger trough. So for example, here is our main larger trough centered over the western half of the US, but notice all these little ripples in the flow that are rotating through the trough. I'll pinpoint them out here for you. There's one right in here. There's one kind of right in here across Wyoming into Colorado, down into New Mexico and West Texas. There's one right in here over the Great Basin down into Arizona, Utah, New Mexico, western Mexico. There's one little one right in here, pretty subtle one. And then there are several more here on the backside of the trough. These are short waves, and short waves are important because they can provide little extra areas of oomph, if you will, little extra areas of energy out ahead of them that can help focus severe storm development in a given environment. So again, these short waves rotate through the main trough. The winds are kind of going like that through the main trough, and these short waves follow this direction and rotate through and out ahead of these short waves. So take, for example, this short wave here. I'll draw the axis through this short wave from Wyoming into Colorado and New Mexico and in West Texas. For these short waves, we want to be right out ahead of these short waves. Just like a regular large-scale trough, we want to be right out ahead of these short waves. These short waves translate through, and right out ahead of them, again, can be somewhat enhanced forcing and somewhat enhanced lifting to help initiate severe storms. Say we had just broad flow without a real trough in it, but we had little ripples in the flow. That can sometimes mean the difference. These shortwaves can sometimes mean the difference between no storms initiating and a lot of storms initiating. For example, take a look out here along the eastern and northeastern US. We're just in a belt of more westerly flow here. But notice we have a little bit of a ripple rotating through the flow. Sometimes that can be just enough to initiate storms in an environment that really doesn't have a large-scale trough to help initiate storms. So always be mindful of these little shortwaves, as they can be very helpful in focusing the severe weather threat in, say, if you have an environment that's all the same, just looking right out ahead of a particular shortwave can be very favorable and can give you a clue as to where the most focused area for severe weather may be. You can also look for shortwaves at 500 millibars. Sometimes shortwaves will be more apparent at 500 millibars than they are at 700 millibars, and sometimes vice versa. So you can use both of these maps to identify shortwaves. For example, here we have a little bit of a shortwave at 500 millibars from Colorado down into New Mexico and West Texas, matching up with the shortwave at 700 millibars that we saw there. So in this example, that shortwave is pretty apparent at both of these levels, but sometimes that's not the case. So if you're looking for shortwaves, definitely look at both the 700 and 500 millibar maps to make sure you are analyzing them as you need to. Down at 850 millibars, we want to be looking for a feature called the low-level jet, or LLJ for short. The low-level jet is basically a belt of stronger winds in the lowest levels of the atmosphere that does a couple of important things for severe weather. Number one, it can help really pump moisture into our area of interest. Usually the low-level jet has a more southerly component to it. And just a side note, winds are described by the direction which they're coming from. So a wind blowing from south to north is described as a southerly wind. As we talked about earlier, that moisture source for most of our severe weather events in the U.S. comes from the Gulf, or at least the southern states in the U.S. So out of the south, when the winds are out of the south in the low-level jet, that moisture gets really efficiently pumped northward into our area of interest to help moisten that low-level environment, provide storms a lot of fuel to work with, and increase instability overall. Number two, it can actually increase low-level wind shear to a level that's favorable for tornadic activity. So when your low-level wind fields are stronger, that tends to increase low-level shear. And as we talked about earlier, thunderstorms are able to produce tornadoes when the low-level shear is on the strong side. Now, there are some special examples where you don't really need a low-level jet to produce tornadic activity, but in the majority of cases, you want to see stronger low-level shear for tornadic activity, and a stronger low-level jet helps in that regard. So on the 850 millibar map, we want to be looking for areas where winds are enhanced, generally above about 30 knots or so. And in this example, we can see that is in place across the central and southern plains from Kansas down into West Texas. You can see those wind barbs are at about 30 knots, 30, 35, 40 knots or so, even 150 knot wind barb there across southwest Kansas. So in this case, we have a nice, fairly expansive low-level jet here, and usually the low-level jet is associated with a low-level cyclone. We're going to talk here in just a second how to identify surface cyclones and low-level cyclones on weather maps. And this example actually does have a low-level cyclone here centered right there in northeast Colorado. Usually our low-level jet is associated with a low-level cyclone, and that is the case here. So you're just simply looking for areas where your low-level winds are fairly strong, usually with a southerly component, and they're going to be often paired with a low-level cyclone. Let's now move on to the surface, and just like the 500 millibar map, the surface map is one of the most important tools that we have to analyze severe weather, because a lot of the features that occur at the surface are extremely critical in the progression of a severe weather event. Before we fully dive in, let's go ahead and take a look at just what all these numbers and symbols mean. For example, let's go ahead and take a look at this station here in western Missouri. So there are a bunch of numbers. All these stations are located at different towns across the U.S., and these stations are equipped with weather instruments. They record data like temperature, pressure, dew point, current weather at the station at the time of observation, pressure change over time, all these kind of variables that are important to analyze in weather observation. But they can be a little bit confusing, so let's go ahead and take a look at what these numbers mean. So the wind barbs work just like the wind barbs work in the upper levels of the atmosphere. The intensity of the wind is given by the flags and staffs, again, a flag is worth 50, a full staff is worth 10, and a half staff is worth 5. So this would be a 15 knot wind. And the direction, again, is given by going through the flags toward the center of the station. So this would be a 15 knot southwesterly wind here at this station. The number at the top left is surface temperature at the time of observation. The number at the bottom left is surface dew point. The number at the top right is surface pressure at the station. Now, this is given in code. If the first digit is between 5 and 9, then we put a 9 in front of this value. So this pressure here at this station would be 999.8 millibars. We always put a decimal between the last two digits, and then the first digit tells us what the leading number is going to be. So this one is the leading number is a 9, so it would be 999.8 millibars. If the first digit is between 0 and 4, then we put a leading 10 in front of the value. So for this station, for example, 022, the first digit is between 0 and 4, so that would be a pressure of 1002.2 millibars. So again, we always put a decimal between the last two digits, and that first digit is going to tell us what the leading number is going to be. So for our station in western Missouri here, this is going to be a pressure of 999.8 millibars. So those are the main values that you'll see on a station plot. You may also see these symbols here between the temperature and the dew point. These represent the present weather that's ongoing at the station at the time of observation. We're not going to go through what all of these symbols mean. This one, for example, this R-shaped symbol here, is representative of the fact that thunderstorms were ongoing at the time of observation. There are dozens and dozens of these present weather symbols. You can find those online anywhere if you just look up present weather symbols. Though you may sometimes see those in station plots on a surface map. On a surface map, we're looking for areas of low pressure, surface lows. Those are our main features of interest, and surface lows are always associated with frontal zones, cold fronts and warm fronts. And those boundaries and the surface low itself can be very critical pieces in severe weather setups. Now, we're not going to take you through how a surface map is actually analyzed, but it would look something like this. We would do an analysis of the pressure values at each station and come up with a map that looks something like this, a contour analysis that looks something like this. Again, these are contours of equal pressure called isobars. So the first thing that we want to identify is where our surface low is located. And basically that's going to be at the center of the lowest pressure contour. So it would be somewhere right in here as analyzed on this map.
Join the Storm Chaser Coaching Discord server and get instant access to a rapidly growing storm chasing community. Once you've joined, you'll be able to chat with our coaches, get your questions answered during weekly live office hours, and discuss strategy in the forecasting and storm chasing forum. You can join the Storm Chaser Coaching Discord server right now via the link in the description.
Now, if you don't have time to do a full surface analysis, if you just are giving a quick glance to a surface map on the morning of a severe weather event, you can identify where a surface low is approximately located by looking for areas where the winds are spiraling counterclockwise around a given center. Winds spiral and rotate counterclockwise around a surface low. In our example here, we can see that is located somewhere there in the far southeast Nebraska, northeast Kansas, northwest Missouri corridor. Notice how the winds over much of eastern Nebraska are out of the north or north-northwest, turning to more westerly winds over eastern Kansas, more southerly flow over northwest Missouri, with more easterly and northeasterly flow over much of southwest Iowa. So at the center of that kind of spiral, that counterclockwise spiral in the winds is going to be where your surface low is located. Also located near the station with the lowest pressure, which would be this one here, 997.8 millibars. And of course, a full pressure analysis, isobar analysis, will give you the best chance of really pinpointing where that surface low is. But if you don't have time to do so, those are some good tips to help you find where that surface low is. In this example here, it's going to be located at the center of that lowest pressure contour there. So we would mark our surface low with a red L. Next, we're looking for fronts, cold fronts and warm fronts, and any other boundaries that are available at the surface. These boundaries are, again, very critical in the severe weather process because they can help initiate storms. We have our troughs that can help actually prime the environment for storm initiation, and then that forcing along these frontal zones where the winds actually come together, that can provide a little bit more focused forcing to actually initiate the storms themselves and set the severe weather event in motion. With a surface low, there is always going to be a cold front and a warm front. A cold front is usually always on the western or southwestern or south side of the actual surface low. And then the warm front is going to be on the eastern or northeast or southeast side of the surface low. So the cold front is always going to trail the warm front. So first, let's take a look at our cold front. Now, the way we want to find out the position and determine the position of frontal zones is through multiple factors. There are multiple ways that we can actually determine where a frontal zone goes. The first of these is through pressure tongues. When we do this isobar analysis, this pressure analysis at the surface, we can sometimes come up with these pressure tongues, these kind of tongues of the isobars here that kind of stick out, very much like a trough in the mid and upper levels of the atmosphere. It acts kind of like a ski jump. These pressure tongues are areas where the isobars kind of stick out a little bit like this. That is a classic sign of a frontal zone. We also have some evidence of a frontal zone through wind shifts. So for example, if the winds are shifting from, say, westerly across one area to more southerly in another area, a boundary is likely in that location between the westerly winds to the west and the southerly winds to the east, because along frontal zones, the winds converge or come together. Those are really the main two features that can allow you to pinpoint where a frontal zone is located. We also can have temperature and moisture gradients. So if temperatures are very cool on one side of a boundary and very warm on the other side, there's likely a frontal zone there. Also moisture. It can be a lot drier on one side of a boundary and a lot more moist on the other. So let's take a look here at our example. Our surface low is right in here, and so let's take a look at our cold front. Again, it's mostly going to be on the southern side or western side of the surface low. We see right here a nice little pressure tongue right there across eastern Kansas into northeast Oklahoma, down even into central Oklahoma. We also see a nice wind shift. Winds across much of Kansas out of the west or northwest, even down into Oklahoma as well, shifting to more southerly and southwesterly here across far eastern Kansas, Missouri into eastern Oklahoma. So there's a clear wind shift in here, co-located with that pressure tongue. And we also have a temperature and moisture gradient. Temperatures in the 50s and 60s back here to the west, temperatures in the mid to upper 70s here to the east. Also dew points in the 40s and 50s back to the west, with dew points in the 60s off to the east. So with frontal zones, you want to see multiple of those factors we talked about be in place where that frontal zone is located. You don't just want to see one of those factors in place and the rest not be there. You want to have multiple pieces of evidence to tell you where that frontal zone is located. So in this case, for the cold front, we have a very well-defined pressure tongue, very well-defined wind shift, temperature gradient, and moisture gradient. So with confidence, we can put the cold front through that wind shift and through the pressure tongue here, down through eastern Kansas into northern and central Oklahoma right in there, and that would be our cold front. Cold fronts are drawn in blue, always connected to the surface low with triangles that are pointed in the direction of motion. For a cold front, cold air is always moving into a region of warmer air, so the triangles would point toward the warmer air mass. Let's try our warm front. Our warm front is always going to be, again, off to the north or northeast, or generally on the eastern quadrants of the surface low. So once again, we're looking for pressure tongues, moisture gradients, temperature gradients, and wind shifts. So right away, we see a little bit of at least several different pressure tongues in here. So right away, just from looking at the pressure tongues, we can't really pinpoint where the warm front is located. We see a little bit of one right in here, one up in here as well. But this northern one may be the one to look for because we have a very well-defined wind shift. Winds here across northern Missouri out of the south, and then we shift to much more easterly flow winds out of the east, southeast to east, northeast here, up into far northern Missouri, southern Iowa. We also have a clear temperature gradient as well. Temperatures shifting from the 70s here across Missouri, central Missouri, to the 50s and 40s up here to the north. Also a moisture gradient, dew points in the mid to upper 60s down here across much of Missouri, dew points in the 40s and 50s off to the north. So it looks like our warm frontal zone is located somewhere in here. Here up to the north may not be the exact one. It might be a little bit farther down to the south here through the southern pressure tongue, because that's where our most robust moisture gradient is. We do see a moisture gradient in both of these pressure tongues here, but the southern one may be the one of note. So the warm front probably is going to go right in here. Now, this is a little bit arbitrary, and it takes a lot of practice, but you'll get the hang of it once you practice a lot with these surface lows and pinpointing these surface lows and frontal zones on surface maps. Warm fronts are denoted by these half circles, again pointing toward the direction of motion. With a warm front, the warm air is going into the region of colder air, so the pips always point toward the cooler air. So that is our basic surface analysis. Why do we need to do this on the day of a severe weather event? Well, these boundaries and the positions of these boundaries can be very critical in telling you where exactly you need to be to target for a storm chase. If you analyze a cold front and that's your initiating boundary for storms, and you analyze it 100 miles off, you're just taking a quick glance, you misanalyze it, that can put you way out of position for being on the right storms. So you really want to get in the habit of really looking at the surface map in detail. You don't have to do this full-blown analysis every single time, but at least looking at your surface map, your raw surface data, finding where those winds spiral around in a counterclockwise fashion. We pinpointed where that was by eyeballing it. The low was somewhere up here in far southeast Nebraska to northeast Kansas. And then your frontal zones, you're again looking for wind shifts, temperature gradients, moisture gradients. We see a clear temperature gradient here, wind shift from more westerly winds to more southerly winds. So there's very likely a cold front somewhere in this vicinity here. Warm front, same thing. We see a very well-defined temperature gradient up in here. And so that is how you would pinpoint those frontal zones and the location of the surface low without actually doing a full surface analysis. Those are your main things that you want to be looking for on the surface map. We also can have other boundaries like dry lines. Dry lines separate hot, dry air to the west from warm, moist air to the east. Dry lines can be very important in severe weather formation, especially on the plains. We can also have outflow boundaries from previous convection, but you're always looking for those clues we talked about. Multiple clues. You want to have temperature gradients, moisture gradients, wind shifts, and if you do a full analysis, those pressure tongues can really help you out in giving you the exact location of where those boundaries are. Finally, let's talk briefly about soundings. I know these diagrams can be pretty intimidating if you're just seeing them for the first time or just getting into severe weather forecasting and storm chasing, but they are one of our most critical tools that we can use when making a forecast, so it's definitely worth inclusion. We're just going to give you some basic tips about how you can tell whether or not a sounding is favorable for severe weather. So basically these soundings come from the weather balloons that are released by the National Weather Service offices every morning and evening. They usually release them at 7 a.m. Central Daylight Time and 7 p.m. Central Daylight Time, sometimes during the middle of the day as well, sometimes around 1 p.m. Central Daylight Time. Just depends on the day. If there's more active weather, they will release more balloons. If it's a quieter day, they might just release one balloon in the morning, one in the evening. So the weather balloons are equipped with instrument packages that radio back data that consists of temperature, dew point, pressure, winds, etc., all the way up into the atmosphere until it pops, basically. What the Weather Service gets back is a bunch of raw data that's manipulated into a nice looking diagram that looks like this. This is an example of a nice sounding that's been compiled by sounding software. After the raw data has come back, this is what it looks like. So the sounding is basically split into two main parts. On the left here, we have the Skew-T, and on the right, we have the Hodograph. We'll start here on the left with our Skew-T diagram. This is showing us the thermodynamics in the atmosphere at that given location that the sounding was released from. This is basically involving our temperature and how moist, how dry, how unstable our air is. So we're not going to go through all the intricate little lines on the diagram, but let's just show you what the main features are. So On the x-axis here, the bottom axis, this is temperature, so I'll put T down there, and this going up on the y-axis here, the vertical axis, that is height given in pressure, so 1,000 millibars, 850 millibars, 700 millibars, and so on and so forth. So this red profile here is the atmospheric temperature. So it's the temperature that the balloon senses as it goes up in the atmosphere. The green profile is the dew point profile. So that is basically moisture that the balloon measures as it goes up in the atmosphere. These two can tell us a lot about how moist and how dry the air is. When these two lines, when the red temperature profile and the green dew point profile are far apart from one another, like you see at this level here, that indicates dry air. When they're closer together, as you see in the lowest couple kilometers here of the sounding, that indicates a much more moist environment. So when those lines are closer together, more moist. When they're farther apart, it's a drier atmosphere. Generally, we want to see fairly deep moisture in the low levels, that temperature profile and the dew point profile fairly close to one another through a decent layer of the atmosphere. Now, there's not any set threshold here, but at least, a kilometer or two off the surface, this is a nice deep moist layer of moisture here in the low levels of the atmosphere. That usually tends to be below a bit of drier air aloft. Now, too much dry air can be a bad thing, but when you have that drier air atop a little bit more moist air, that can create instability. Now, the other piece of this is this brown dashed line here. That is the parcel trace. So think about the air at the surface. Think about taking just one sort of hypothetical box of air. Let's take a cardboard box, get rid of the sides of the box, but we have a box of air that's a box that's just full of air at the surface. The parcel trace is basically the temperature that the parcel would take on if it were to be released into the atmosphere and be able to rise on its own. We want the parcel then to be warmer than the actual environment. So when this parcel trace, this brown dashed line here, is to the right of the environmental temperature profile, the red profile here, the atmosphere is unstable. So for all of this distance here into the atmosphere, we have instability because the parcel trace is to the right of the temperature trace. That means at all this level where I've shaded in pink, that parcel would be able to rise on its own. Therefore, that part of the atmosphere is unstable. When the parcel trace is to the left of the temperature profile, like you see right in there, that is some semblance of capping. That means that the parcel is colder than its surrounding environment and therefore will not be able to rise on its own. For severe weather, we want there to be instability throughout the entire atmosphere. We want there to be the situation where a parcel can really rise on its own throughout the entire atmosphere. Now, it is somewhat good to have a little bit of this cap in place early on in the day, going through the morning into the afternoon of a severe weather event, because that can actually hold storms off from firing and allow more and more instability to build. Once that cap is broken later in the afternoon through things like sunshine, warm air, moisture transport, cold air transport aloft, things like we talked about earlier in episode 1 of this series, that can actually allow the cap to break or erode, and then the environment at that point is fully unstable. So again, just to summarize here, we want the environment, we want that parcel trace to be to the right of the temperature profile throughout the entire atmosphere. And we don't want to see any of these once storms are able to initiate. We don't want to see any of that capping left, but capping can be good early on in the event through the morning and into the part of the afternoon to help build more and more instability in the environment. Let's move over to our hodograph now. This is basically just a plot of all the winds in the atmosphere. So it's a little bit difficult to simplify this down, but basically think of this instead of being a regular graph that has X and Y coordinates like our Skew-T. It has X coordinates of temperature on the horizontal axis and Y coordinates of height in pressure on the vertical axis. Well, that's not what this hodograph is. This is basically a circular graph that is basically made up of magnitude, these circles here, and angles. So we basically draw the winds, draw the wind vectors as kind of arrows. So basically that lowest point of the hodograph is our surface. Our surface winds are out of the southeast at 10 knots. You see that wind barb there. So basically this surface point is showing us where our winds are there at the surface. So if we were to draw an arrow there, that point at the end of that arrow would be what is plotted on the hodograph, and then we just connect the dots all the way up through the atmosphere. Now, just keeping this simple, the shapes that you want to see for the hodograph for severe weather, you want to see more elongated hodographs, more lengthy hodographs. If you see all of these points kind of on top of one another, and you have just kind of a mess of lines that really is very small in its extent, that means that your deep layer wind shear is on the weaker side, which is not favorable for severe storms. When you have longer hodographs like this, that means that you have stronger deep layer shear, which is able to allow the storms, as we talked about in episode 1, to become tilted and rotate and organize themselves into severe storms. For tornadoes, we want to see more of a meat hook type shape. So we want to see some curvature in the lowest levels of the hodograph, which is this red portion here. That's the nice thing about this sounding source I'm using from the Storm Prediction Center. They color code these different segments of the atmosphere. So red is the lowest 3 kilometers, the light green is from 3 to 6 kilometers, and so on and so forth. So we want the portion in the lowest kilometer or so of the atmosphere to have some nice curvature to it in the clockwise direction. As you see here, this is a good example of that. Nice clockwise curvature in the hodograph. That means we have strong low-level shear, which is favorable for tornadoes. Again, there are some special cases where we don't see strong low-level shear for tornadoes, but for the most part, this kind of meat hook type shape is more favorable for tornadic activity than a straighter hodograph. If we have just a straight line hodograph, that favors more large hail and damaging winds, not so much of a tornado risk. So those are just some basic tips to help you at least identify if a sounding is favorable or not favorable for severe weather. Again, we want to see an unstable environment where our parcel, the brown dashed line here, is to the right of the red profile. We want to see fairly deep moisture so that the temperature and the dew point profiles in the atmosphere pretty close to one another up through the lowest couple kilometers there of the atmosphere, and underneath some somewhat drier air aloft to help build that instability. And then for our hodograph, we want to see longer hodographs, a longer profile overall. For tornadoes, we want to see that hodograph have a lot of curvature in the clockwise direction in the lowest levels of that hodograph. And for large hail and damaging winds, typically we see that with more straight line hodographs.
Remember to check out those links in the description below, and then watch another video.